this is an introduction to work. The section is about a concept from physics called work. We are going to talk about what work is in everyday terms. We'll discuss what work means to physicists. It's defined in terms of force and displacement. Then we'll just discuss what force means intuitively, and then how we calculate or measure force using quantities. We'll talk about SI units versus English units, and what the appropriate units are for force, mass, and work in both systems. We'll talk about work due to a force that varies from point to point, and Hooke's law. And then I'm going to introduce the two types of problems that we tend to focus on in Calculus 2. These are the work done in lifting a rope or cable to a certain height, and also the work done in emptying a tank. This video won't include examples of these two types of problems, but we'll introduce the idea, and then we'll talk about these two types of problems in general before we get into some examples in the other videos. Okay, so when you hear the word work, you might even think of Calculus 2. You know, work is about effort. I mean, that's the way we tend to use the word work. We say, if somebody says that's a lot of work, they mean that they have to put in a lot of effort. You might say Calculus 2 is a lot of work, and you'd be absolutely right. But in physics, it's defined a little differently. In physics, work is defined to be the dot product of force and displacement. Both of these are vector quantities. They have magnitude and direction. Because if I'm taking a force of a certain amount, like so many pounds of force, and I'm applying it in one direction, it's going to have a different effect than if I'm applying that many pounds of force in a different direction. So the direction matters. Displacement is also, it's a vector quantity. It is a change in position. It's the position that you end up in minus the position that you started from. So that's that change. And we take the dot product of those two guys and we get work. If you don't know what dot product means, that's okay. At this point, all you need to know is the dot product of two quantities is the magnitude of the first times the magnitude of the second times the cosine of the angle between them. And we'll talk about what this means physically when we look at a little picture down here. So let's say you have some box or trunk that you're trying to move, and I can't draw it very well, so I'll just draw a box that says trunk on it. Okay. Now let's say you're applying a force at an angle like this, and it's making an angle of theta with the horizontal, and that trunk is moving through some displacement d. So that's our displacement vector. It starts here, and then it ends up over here sometime later. So this is where our trunk will be after we have applied our force. Well, according to this formula for work, I just take the magnitude of this force times the magnitude of the displacement, and I multiply by the cosine of the angle between them. Now the angle between them is actually this angle theta. It doesn't look like it's the angle between them, but if I draw my force and my displacement with the same initial point, my displacement would look like this. You see that that angle with the horizontal is the angle between the force and the displacement. You say, okay, well, what does that have to do with anything? Well, let's talk a little bit more about what work means. I'll draw another picture without that displacement vector. So I've got my trunk, and I'm moving it through some displacement d, and I'm acting on it with a force like this, with And the angle that that force is making with the horizontal is theta. Well, some of this energy is being wasted. Think about moving. If you are pressing down on a trunk like this and trying to move it across the room, you're wasting a lot of your energy and effort. You're wasting all of this energy and effort right here. You're pushing the trunk into the carpet, and that's not helping you move it at all, is it? The part of the force that's actually helping you to move this trunk across the room is the part of the force that's parallel with the displacement. So if I take this force and I break it up into two pieces, one that's parallel to the displacement and another that's perpendicular to the displacement, the one that's parallel to the displacement is actually doing the work. It's actually moving this trunk across the room. Well, the magnitude of the force that is parallel to the displacement, well, that's adjacent to theta in this right triangle. So the adjacent side is the magnitude of the hypotenuse, which is the magnitude of the force, times the cosine of theta. And that wasted energy, that's the magnitude of the force times the sine of theta. So the amount of work done in moving this trunk across the room, according to the dot product formula here, is the magnitude of the force times the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. But you can look at it this way. We're taking the magnitude of the force that's acting in the same direction as the displacement, and then we're multiplying those, and we're calling that the amount of work done. So work is force, and I'm going to write in the direction of displacement. Well, let's say the amount of force that is, well, I'm going to say this in the direction of displacement for right now. Times the distance that that trunk or that displacement is moving us through. And this is the magnitude of F times cosine of theta. And the distance, if we're traveling along a line like this, is just the magnitude of the displacement. So that's work. Now if my force is constant and my displacement is constant, I just multiply the two quantities together. So let's say here's my trunk, and I'm applying 30 pounds of force at this angle. And the angle with the horizontal is 45 degrees. And I'm moving my trunk, let's say 10 feet, because I'm trying to move it across the room. Well, according to our physical formula for work, so I'm not talking about the amount of effort involved, but I'm talking about this quantity, the amount of force in the direction of the displacement, or times the distance. Well, it's just going to be the length of this vector times the length of this vector. Since they're both pointed in the same direction, the work is just the product of those two numbers. If they were pointed in opposite directions, the work would be negative. And I'll let your physics teachers talk to you about what negative work means. So this side of the force vector is adjacent to the 45 degrees, so it's going to have a magnitude of the magnitude of the force times cosine of 45, which is 30 times square root of 2 over 2. That's pounds. So that's 15 root 2 pounds, and I'm multiplying it by this many feet. So work is, I've got 15 root 2 pounds of force, times 10 feet. Feet times pounds, I know it seems strange, that's called foot-pounds. Those are units of work. And according to my formula, that's the amount of work that was done in moving this trunk through this distance with 30 pounds of force. Now, if I wanted to do the maximum, if I wanted to maximize my work so I wasn't wasting so much of my energy, instead of applying my force at this angle of 45 where I'm wasting 15 root 2 pounds of force just pushing my trunk into the floor, I could do my 30 pounds of force just acting this way. And then it would be a lot easier. If you get right behind the box, you can push it across the room. They're going to be all lined up, and you're just going to take 30 times the 10, and you're going to get 300 foot-pounds of force instead of this 150 root 2. I said foot-pounds of force. It's foot-pounds of work. Excuse me. Okay, so that is the definition of work in physical terms. Now, I've been talking about force as if we knew what force was. I guess I should have discussed that first. Force, intuitively, is a measure of like how much we're pushing or pulling on something. Now, according to Newton's second law, we define force to be mass of the object times the acceleration of that object. So the force being applied to something is that mass times the acceleration, and that's our force. Now, in your physics classes, you probably have seen two sets of units. SI units is what we tend to use in our science classes, but if you live in the United States, we use English units a lot as well. In SI units, mass tends to be measured in grams or kilograms. Kilograms is what we see most of the time. Of course, we could change the prefix. Acceleration is measured in meters per second squared. And we abbreviate that this way. Let's see. Distances, displacements tends to be measured in meters. And force is a mass times an acceleration, so it's a kilogram times a meter per second squared. And we call that a Newton. 1 Newton of force moves 1 kilogram, 1 meter, at an acceleration of 1 meter per second squared. It's just abbreviated by an N. Now, in English units, we use pounds as our measure of force. And distance tends to be measured in feet. Acceleration in English units is feet per second squared. And mass is measured in slugs, but we almost never talk about slugs. We don't spend a lot of time talking about slugs in physics class. We just go straight for the pounds. In physics class, we do talk about mass and multiplying mass by acceleration, especially acceleration due to gravity. And then you multiply those two together and you get newtons. But over here, acceleration due to gravity is already included in the pounds. So as soon as you hear pounds, know you're already dealing with force. If you hear kilograms, then know that you're talking about a mass, and in order to get a force, you have to multiply by an acceleration, usually the acceleration due to gravity. And we're going to see all of these in applications more and more. Oh yeah, okay, let's take these units and go to work now. Work is force times distance, or force dotted with displacement. So you're going to use units of force times units of distance in that particular coordinate system. So work in SI units is a Newton. That's a unit of force times a meter. And a Newton times a meter is called a joule. It's also a measure of energy, which actually makes sense in our intuitive definition of work. We think of something being a lot of work if it requires a lot of effort. I think just following that train of thought, if something requires a lot of energy, we would think it also requires a lot of effort and it feels like a lot of work. So joules are measures of energy. They're also forces times distances. In English units, our distances are in feet and forces are in pounds. So work has units of foot-pounds. I know it seems strange. It's not foot per pound, but it's foot-pounds. Okay, so those are our units of work. So we've talked about what work is in everyday terms. It's just effort, or thinking about using a lot of energy. But in physics, work is force dotted with displacement, or the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Or you can think of force acting in the direction of displacement, and that is the force times cosine of theta multiplied by the distance it moves through. Sorry, it's all very small. So that is what work means in physics class. And force is, again, just a push or a pull, and it's given by Newton's second law. It's mass times acceleration. And if you hear feet and pounds, know you're in English units. Work is in foot-pounds. If you hear about kilograms, meters, and newtons, you're in SI units. Those are our standard scientific units. And work is a Newton meter, or a joule. Okay, now this formula works as long as our force is constant over the entire displacement, and that displacement vector is not changing. If the force is changing at all as a function of x, if you have different amounts of force at different x values, or you have different displacements for different forces, then this formula, it can work, but it can't work without calculus. This works very well whenever you've got a constant force or a constant displacement. But if the force is variable, we're going to need some calculus. And Hooke's law is a particular example of that. So let's look at an example problem. Let's say I want the work required to lift a, let's say, 1 kilogram book, let's say 4 meters off of the floor. So maybe you're putting it on a bookshelf. You might ask yourself, is calculus required here? So maybe this is our bookshelf. This is 4 meters. And I've got my little book on the floor over here. And I just want to put it up there. Question is, how much work is required to lift that book and put it on the shelf? Now, we're not worried about this horizontal distance. We're just thinking about taking this book and lifting it up 4 meters. Well, I don't think there is any calculus required. Work is just going to be force times distance. Because we're assuming that our force and our displacement are acting in the same direction, so we can just use distance. And force is mass times acceleration. So we have mass times acceleration times distance now. And my mass was 1 kilogram. The force acting on that book is its weight. So that's mass of 1 kilogram times acceleration due to gravity. Acceleration due to gravity in SI units is approximately 9.81 meters per second squared. So we're going to take 1 kilogram and multiply it by 9.81 meters per second squared. That's going to give me 9.81 newtons, because a kilogram times a meter per second squared is a newton. Oops. So that together gives me that, and then I want to multiply by the distance I'm going to move that book through. I'm moving that book through a distance of 4 meters. So that's my distance and that's my force. So I just multiply them together. And I get, well, that's about 10. I'm just going to estimate. This is a very rough estimate. So if that's 10 times 4, it's about 40 newtons times meters, and a newton meter is a joule. So it's about 40 joules of force required here. So this is actually very simple. It doesn't require calculus. I just do force times distance, and that's it. What if I am like lifting up a weight? So let's say we want the work required to lift a 30-pound weight 5 feet. Well, again, 30 pounds and 5 feet are not changing. This thing weighs 30 pounds the entire time. It's going to be moving through exactly 5 feet. So if I've got a 30-pound weight right here, and I'm moving it through 5 feet, well, my distance is 5. My force is the 30 pounds, because remember, pounds are units of force. So work is just force times distance. So 30 pounds times 5 feet, which gives you 150 foot-pounds. I know it seems strange, but those are units of work. We've got 150 foot-pounds of work that we're done. Now, neither of these required calculus at all, because I've got a constant force as I'm moving that object through a constant displacement. That 30 pounds of force is acting on that object through the entire 5 feet. And over here, my 9.81 newtons of force is acting through the displacement of 4 meters the entire time. So no calculus is required in either of these cases. Now, if we have a variable force, let's say our force at position X is given by f of x. Well, every time I want to find a work done by this force acting on an object moving through a particular distance. So here's my object, and now I have this little force. I'm making it sort of wavy like this because it's varying. Okay, so that force is changing from moment to moment. Well, the way I would find the work is I'd find the work at one moment, I'd find the work at another moment, find the work at the next moment. And this is going to be my force in that moment times the displacement in that moment, or the distance traveled through in that moment. So I'm taking the force that's acting at a particular x value, and I'm multiplying it by a tiny change in x. That's the distance we're moving through. So that's the work on one piece for one x value. We want to do this n times for n different pieces. So total work is the work on the first little interval plus the work on the second interval plus the work on the third, all the way through the work on the nth interval. Well, we know that's a Riemann sum. So this is the sum as I goes from 1 to n of the force acting at a particular x value, that's the force at that x, times the distance that that object is moving through. And if I want the exact work, we want all the x values. So we take the limit as a number, oops, that should be a delta x. Number of pieces goes to infinity. And that's an integral. So if we start at x equals a, and we end at x equals b, the work done by a variable force f of x is the integral from a to b of f of x, which is a force, times a tiny displacement or a tiny distance, dx. So we could use that. So here's an example. So we'll say, suppose a particle at position x experiences a force of f of x equals x cubed plus 4x. Someone might ask you, what work is done in moving that particle from x equals 1 to x equals 2? Well, I think we know we're going to start at x equals 1, we're going to end at x equals 2. So we've got that. The force acting at x is x cubed plus 4x. We're taking that force and we're multiplying it by a displacement, delta x. So if I can evaluate this integral, I can find the work done. Very simple. So work is, in this case, the integral from 1 to 2 of x cubed plus 4x dx. We're going to use the power rule, add 1 to the exponent, divide by the new exponent, bring the 4 down, add 1 to the exponent, divide by the new exponent. By the fundamental theorem of calculus, we take the antiderivative, we evaluate it at 1 and 2 and subtract. 4 divided by 2 simplifies to 2. So when I substitute in 2, I get 1/4 of 2 to the 4th plus 2 times 2 squared. Then I substitute in 1, I get 1/4 plus 2. And that's our answer. That's the amount of work done. That's 16 divided by 4. So that's 4 plus 4 times 2 is 8. And over here I've got 2 1/4. So that's 8 over 4 plus 1 over 4 is 9 over 4. So I've got 12 minus 9 over 4. So that's 48 over 4 minus 9 over 4. So that's 39 over 4. All right. Or if you prefer, 4 goes into 39, what, 9 times? So this is 9.75. And I'm not sure what the units are because I didn't tell you what the units of this original force were. I just told you that the force was this at position x. So we're going to take the units of force and we're going to multiply by the units of this displacement. If this is in newtons and that's in meters, this is 9.75 newton meters, and a newton meter is a joule. Okay. Another example of a variable force acting on an object is due to Hooke's law. And Hooke's law says this: the force required to move a spring x units past its natural length is given by kx. So the force is equal to kx, and k is a property of the spring. It's called the spring constant. Okay. Now, as long as we aren't stretching too far past the natural length, this is predictable. This is how it works. So maybe we've got a spring like this, and its natural length is right here. So that's where it would sit. But if I stretch it out a little bit, instead of having it here, but I stretch it out to here. So I'm stretching it X units past its natural length. As long as I don't go too far, so I don't break my spring, there's going to be a restorative force. If I pull it this way, which way is the spring going to bounce back to? I hope you said it's going to go that way. If I pull this way and I let go, it's going to go back that way. So the force acting on it is going to go this way, and it's going to be equal to K times X. Okay, so that's Hooke's law. So here's an example. Oops. Let's say a force of, let's say 50 newtons is required to hold a spring that has been stretched from its natural length of 8 centimeters to a length of 13 centimeters. Okay, so they tell us that, and then the question says, how much work is done in stretching the spring let's say 2 more centimeters. So from 13 centimeters to 15 centimeters. Okay. Well, this is an example of variable force, so I know that I'm going to evaluate the integral from x equals a to x equals b of the variable force times dx. But this information up here, that's going to be enough to help us find our spring constant K. So they tell us that a force of 50 newtons is required to hold a spring that has been stretched from its natural length of 8 centimeters to a length of 13 centimeters. So here's my spring. It normally goes out to 8 centimeters. But instead of going out 8 centimeters, we're going quite a bit further out here to 13 centimeters. So this distance x that it's been stretched past its natural length is 5 centimeters. Now the restorative force, because I've stretched it 5 centimeters past its natural length, is going to be some constant times that 5 centimeters, that constant times 5, that's going to be my force. And in order to counteract that, this force of 50 newtons is required. Like if it's pulling this way, we need to have an equal and opposite force pulling that way so that it actually just stays in one place. So if they're telling us 50 newtons is required, they're saying you've got to pull with 50 newtons in this direction to compensate for that spring pulling back in the opposite direction. So our spring is pulling back at a force of kx, and we're told to balance that, we need to add 50 newtons of force on this side. Say, okay, well then, if my x is 5, if that's the case, what does k have to be? Well, kx has to balance this 50 newtons, so kx must be 50 newtons. So really, I'm just substituting into kx equals f. and I'm treating this as a magnitude of the force rather than the vector itself. And x is 5 centimeters. Now remember what a newton is. A newton is a kilogram meter per second squared. So the fact that this is in centimeters and not meters is a little bit of a problem. So we might want to convert from centimeters to meters in order to find K. That's actually pretty easy. Centi means 100. So if I'm trying to get from centimeters to meters, turns out all I have to do is multiply by just the right thing. I want centimeters down here and meters up here. And this has to be equal to 1. Since centi means 100, it turns out that there are 100 centimeters in 1 meter. So if I want to figure out how many meters 5 centimeters is, all I have to do is multiply straight across like this. You probably did this in your chemistry classes if you've taken chemistry in college. This is called dimensional analysis. I'm just multiplying so that the units I don't want cancel and that the units I do want are in the numerator. So 5 divided by 100 is going to give me 0.05 meters. And that's what we want here. Instead of using these centimeters, for dimensional consistency on both sides, I want meters over here and meters over here. This is going to be 0.05 meters equals 50 kilograms times meters per second squared. And then we're going to divide both sides by 0.05 meters. Those reduce, the meters reduce, and now I've got 50 divided by 0.05. That's my K. Oops. And the units are kilograms per second squared. Now, if you want to get rid of this decimal in the denominator, we can multiply numerator and denominator by 100. So that's going to give us 5,000. We're adding 2 more zeros, and we're dividing by 5. So our spring constant is 1,000 kilograms per second squared. Okay, we did all of that work in order to find K. Now that we know K, we can find the work done in stretching from 13 centimeters to 15 centimeters. Now careful here, we're not going from x equals 13 to x equals 15. X is the distance that we've extended it past its natural length. At 13, x was 5 because our natural length was 8. To get from 8 to 13, I need to add 5. Now to get from 13 to 15, that just means I'm going to go 2 more centimeters, right? I'm really stretching it now. So the new x value at this point is that 5 plus that 2, so it's 7. And we're going to integrate the force, which is K times x, with respect to x. And we just found out from our previous work that if we are stretching the spring by 5 centimeters with a force of 50 newtons, then the spring constant must be 1,000 kilograms per second squared. Oops, that should be an x, not a k. Now we just anti-differentiate. Add 1 to the exponent, divide by the new exponent. Don't forget your 5 and your 7. So we get 500x squared, evaluated from 5 to 7. So that's 500 times 49 minus 25. What's 49? Oops, you guys can't see that. It's 49 minus 25. I hope you said 24. Okay. And so that's 500 times 20 plus 500 times 4. So this is 500 times 4 is 2,000. And 500 times 20, it's 10,000. And so we get 12,000. All right, and what are the units? Well, this is a kilogram per second squared. Then we're multiplying by x, which is a distance, so that's a meter. So this is a kilogram meter per second squared, so that's a newton. And this is a meter, it's a newton times a meter. So these are 12,000 newton meters, and newton meters are joules. Okay. So that's a variable force. Now, most of the problems that you will see both in your homework and on your tests and quizzes are not the types of problems that we just worked through. But they are problems that involve either a variable force or a variable distance that's acting on a part of an object. So these are the types of problems that you're going to see on your tests and in your homework primarily over work. We're frequently going to take a rope or a cable. It may or may not have something at the bottom, and we're going to find out how much work is required to lift that rope or cable through a certain distance to a certain height. And we're also going to look at the work required to empty a tank. So I'll do that in the next couple of videos. But I hope that you understand this introduction to work. Work is the dot product of force with displacement, which just means it's the force acting in a certain direction times the distance that we're moving through. And then we've got to worry about all of these SI units. Now there are some cases, like these two cases, where calculus is not required. I literally just take the force and I multiply it by the distance. Now if somebody gives me a mass, I've got to multiply by acceleration due to gravity. So as soon as I see those kilograms, I know I have to multiply by the 9.81 meters per second squared. That should not be just a second, meters per second squared, in order to get force. Now, if I'm in English units, forces are going to be given in pounds. Nobody's going to tell you that the mass is so many slugs. They're always going to give you a force in pounds. Here, gravity's already included in that. This is already the number of slugs times acceleration due to gravity in English units. So we just take the number of pounds and we multiply it by the number of feet to get foot-pounds. Now, if our force is variable, like the force due to a spring, the restorative force of a spring, work is just the integral from A to B of that force, which depends on x, times that tiny displacement dx. Now again, most of your work is going to look like these two. We're going to have rope and cable problems and tank problems, and I'll show you how to do a few of those in the next video.